Hello student, to the Foundation of Classical Electrodynamics course. So, under module 3 we have lecture 58 today, and we will going to discuss the torque and potential energy of the magnetic dipole, which we discussed last year also, and then we discuss the magnetization. So, we have class number 58. So, in last class our topic was a current loop in an external magnetic field. So, suppose we have a magnetic field and we placed a current loop like this, where current is flowing I, and so this is the axis here, and the torque that we are going to experience by this system was N is equal to M cross B, that we figure out, that we derived, where M is the magnetic dipole moment, is the magnetic dipole moment. And normally it is defined like current into area. Okay, so that is the structure we had last day. So, if I try to understand the torque, then this is basically the torque. So, the torque on the planar, so if I write the torque on a planar current loop, then this is the value, we already write it, that this should be M cross B. Now, if I try to understand this, suppose in this is the applied magnetic field, this is in this direction. So, the current loop, suppose it is like this, this is the current loop carrying the amount of current, say I. So, this is carrying a current, say I. So, since it is carrying a current I, the direction of the magnetic dipole moment should be along this. So, this is the direction of the magnetic dipole moment, and the torque, the force that we are going to experience by the system should be equal and opposite, and that is, this is the force that will experience here, and since the current is moving in the opposite direction in this, so I will have another force that gives rise to a torque, and the direction of the torque should be along this. This is the direction of the torque vector n, which is m cross b. This is m, this is b, and m cross b is the perpendicular. So, this is the way I am in the magnetic the loop which behave like a magnetic dipole will experience a torque under some external magnetic field. Now, what should be the potential energy that we also need to discuss here. So, the orientational potential energy, what is orientational we will going to discuss later. The orientational potential energy associated with this torque that is simply u equal to minus of m dot b. It is exactly the same expression, same kind of expression that we have in electrostatic when the dipole is placed in a external electric field, and the potential energy that is stored to that dielectric was that amount. So, you need to do some work to orient these things, and that was simply P dot E, and P was the dipole electric dipole moment and E was the electric field. Only you just replace P to M, the magnetic dipole moment, and electric field to magnetic field B, and we will get the result. So, we can discuss this result. So, the potential energy is here the work done by the torque during the infinitesimal rotation of dipole. So, how is that? So, let me draw it. So, this is the top view I am having. So, this is the direction of M, and if it is rotating to another direction, then this is dm, and this is say m plus dm, and the angle that is rotating is say d theta. So, due to the torque, what happened that if you see in this figure, so these things will go to rotate because of the torque. So, this m whatever is here now having a different orientation, and current loop will slightly move, and that basically gives the amount of work done by the torque, and that will be stored as a potential energy. So, that we are going to calculate. So, the d theta here, if I consider this to be a vector that is perpendicular to the plane, and we can have the work done which is du is minus of torque and d theta vector. That is the amount of work done by the torque. Now, here you should note that this dm is simply d theta vector cross m vector. So, I can write here this is as n is m cross b, and that should be d theta, and I can have these as a dot b cross c is b dot c cross a, so and c dot a cross b. So I can write this as minus of d theta cross m and then dot b. So this quantity is my dm dot b. So this is du. So eventually we can have u is equal to minus of m dot b. This is the amount of potential energy that this we called orientational potential energy associated with this torque. So let us discuss a bit about the orientational potential energy. What I try to mean is, so before that let us draw the two cases. One is the, so for electrostatic what we had, so let me draw. This is say electrostatic, and this side I have magnetostatic, and side by side I want to discuss. So the electric field suppose is in this direction for electrostatic, and we have a dipole sitting here with the say minus q to plus q, and the torque that was generated is along this direction. That was the torque. We also calculated the torque in placing the electric dipole in external electric field. So this is the electric dipole. Okay. So and that is in this direction we had P. So this is the direction of P. So from here to here, so that is the direction of P, dipole moment. Now in magnetostatic what we have, magnetostatic, the magnetic dipole can be replaced by the loop, and this is the loop, current loop. And the current is flowing like this, this and this, and the value of the magnetization, the value of the magnetic dipole moment is along this direction. This is m, and the B is along this direction. This is B. Okay, it should be perpendicular. So my drawing is so let me draw it once again. So, B is roughly this, and the torque that one can expect is along this direction, and that is N. Current is flowing here, and that is N. Now, this is the two case, and for that let us now discuss what is the meaning of orientational. So, in this case we had something called orientational potential energy that eventually mean that which is equal to the work. This is equal to the work that must be done by the dipole moment F, dipole moment M from the orientation of zero energy when we have a zero energy, when M is perpendicular to B to any other orientation keeping this mod of M and then mod of B and mod of R fixed. So, we just change the orientation by applying the torque. If you just change the torque so that there is a change in the orientation, magnitude of M should not change. So, if B and M are, so B is a constant, so it will be in this direction only, and M now in perpendicular to B in this figure. So, that tells us that B and M are perpendicular, but I can make a torque, and due to that there is a change in the orientation, and this change in the orientation can be considered to be the orientational potential energy that you have in magnetostatic. With respect to electrostatic, it is slightly different, because in electrostatic what happened, that the potential energy, I mean in this case what happened, that the potential energy is in general it appears because it is equal to the total work that must be done to bring the dipole from infinity. So, here we are not doing that kind of thing, rather we are just orient this dipole against this torque N and make a orientational potential energy. Okay. So, now after that we will discuss magnetization. So, that is the another topic today that we need to cover. So, the next topic is magnetization. So far we are dealing with the problem where magnetic field is calculated mainly in the vacuum. When we use the Biot-Savart law and when you use the Ampere's law, whatever, then the magnetic field that is produced in vacuum. But if we placed a matter in a magnetic field, suppose we have a magnetic field here, and this is the magnetic field lines, and I place a matter here, a chunk of magnetic matter. So, some sort of orientation it can. So, the dipole, the magnetic dipole will going to be oriented by this magnetic field, exactly like the polarization we had in electrostatic problem. So, we have the alignment of this magnetic dipole moment or magnetic dipoles. So, because of that we will have a certain property in the material, and that is called the magnetization. So, if I want to write it in words, so in presence of a magnetic field, the matter becomes magnetized. That means the tiny dipoles, magnetic dipoles, will have their alignments. Along some direction. This is called the magnetization. So, the alignment, there will be some alignment of the magnetic dipole moment, there is some alignment of the tiny magnetic dipole, and we have the magnetization. So, we define few things like big M, which we call the magnetization, which is equal to magnetic dipole moment per volume. Magnetic dipole moment per volume. So, and this is called magnetization. Like polarization, it is called magnetization. So, magnetization is the magnetic dipole moment per unit volume, like polarization. Polarization, electric dipole moment per unit volume, magnetization is like that. So, here we have an interesting concept called the bound current, like in polarization case, electric polarization case. So, that we are going to explore. So, bound currents. So, the vector potential for single dipole, the vector potential for a single dipole, we calculate that, and that is A, I write dipole to make sure that it is a vector potential for the dipole, and this is mu 0 divided by 4 pi, and then it is m cross uh, m cross unit vector r divided by r square, where r is r minus r prime. That we know. So, now if I let me draw that, then maybe that these things will be clear. Suppose we have a distribution of dipole here and have a small element and had a coordinate system, and suppose this is my r and this is the location from here to here. This r prime and this point is r. So, here it is a small, so this is the dipole moment of this small tiny region and dv prime is the small area. So, in the volume element, so in the volume element dv prime, we have dipole moment so m is a dipole moment of a single dipole, but I have a volume dv. So, in this dv, the total amount of dipole moment one can have is simply m multiplied by dv prime, because m is the dipole moment per unit volume, and if I multiply it by the volume, then we have the total dipole moment is this. So, the total vector potential, if I want to calculate here, due to this entire structure having the distribution of the magnetic dipole, then the total vector potential can be represented as the total vector potential is how much. I need to integrate it because it is a total. So, I have A produced at some point r is mu 0 divided by 4 pi, and then integrate over entire volume, where the small element I have the dipole moment as m cross r divided by r square and dv prime. That should be the total. Now, I can make use of when r is r minus r prime according to our notation. So, now we can have the divergence of 1 by curly r is equal to unit vector r curly r divided by r square. So, that I will going to use because I am having a term unit vector r by r square. So, I can write my A then function of r in this way, mu 0 divided by 4 pi, and then I integrate it like 1 by I integrate it m at r prime, and then cross the gradient of 1 by r and then dv prime. Now, I can make use of the relation, that is grad curl of, so this I can write in this way, that mu 0 divided by 4 pi, and then I can have like 1 by r and then this cross m dv prime and minus mu 0 4 pi integration cross m by r dv prime. If I expand this quantity, then I will get this term plus this term. So, that this term is this minus this. So, that I simply write here, and then I can have this. So, the next I will write like mu 0 4 pi, and then this is the volume integral, and 1 by r, then curl cross m dv prime, the same term, but here I am going to use something, a vector identity. Let me first write and then I will show what is the vector identity, and that is m r prime divided by r cross ds prime. So, the identity we use is this one. So, this is one of the problem in Griffith's book. So, we have used the identity, and the identity is, if I have a vector field say G, curl cross G dv over V is equivalent to minus of closed surface integral. So, I should have a closed surface integral here, minus of closed surface integral, and then G cross, not A, I am using the vector field G. So, G cross ds. So, I use this vector identity to get from this to this expression to this one. So, then after doing that, I define these currents, bounds current. One is the bound current density, and that is JB, and that I defined at this cross curl of M, which is function of r prime, and dropping the so simply I can write it is a curl of M, just dropping the this prime notation. So, that is one definition, and this is called the volume bound current density. Similarly, I can have another term KB, which we have like M cross N by definition, and this we call the surface bound current density. So, based on this definition I can rewrite my A, and I can write my A in this way. My A should be now mu 0 divided by 4 pi, and then integration current density, volume current density, that should be function of r prime divided by r dv prime plus mu 0 divided by 4 pi, and the surface, total surface integral, then surface current, bound current density, function of r prime divided by r d s prime. Okay, so I think I should stop here because I don't have much time. So, in the next class what we do, that we will discuss more about this bound current density and surface bound current density, volume bound current density and surface bound current density, and the physical significance of that. So, with that note I would like to conclude today's class. See you in the next class.